Python is slow for repeated execution of low-level tasks. For every operation, Python has to check the type of the objects which are being operated. This leads to an overhead that is larger and larger in loops of many iterations. To avoid the overhead, NumPy provides methods for repeated operations, which are implemented as compiled code in the lower-level language C. These are the so-called universal functions, which are arithmetic operators, comparison and bitwise operators, trigonometric, exponential, and logarithmic functions, and many more. Besides universal functions, NumPy has also fast functions to compute statistics on an array. These are aggregation functions, such as sum, mean, standard deviation, and so on. Let's now estimate the value this series converges to. We compare the speed of three approaches: a for loop in Python, a for loop in Fortran, and vectorized operations using NumPy. We define the function funcLoop for the simple Python loop, and the function funcUfunc for the vectorized operation on a NumPy array. Here we use pip to install the Fortran Magic extension, which allows us to compile Fortran code and use its symbols in the Python session. We begin a new cell with %% and define the subroutine funcFortran. When we run the cell, the code is compiled, and the subroutine is automatically imported and available as a function in our Python session. When we measure the execution time using the magic command timeit, we see that the Python for loop is approximately 100 times slower than the NumPy approach and the Fortran code. That's because in lower level languages like Fortran or C, the type is checked only once before execution. Now let's apply one of the universal functions and add two 1D arrays together. We see that the entries are added element-wise. What happens if we add a row matrix to a column matrix? The smaller shape of each array is augmented to match the larger shape of the other array. The row matrix is stacked vertically 4 times, while the column matrix is stacked horizontally 5 times. This behavior is called broadcasting and applies for all universal functions, for example when we multiply a vector by a single digit or when we divide a matrix by a vector. The operation between a matrix and a vector will succeed if they have a dimension of same shape. Here we see that it is possible to add a row vector of size 4 to a 3 by 4 matrix, whereas we get an error when we try to perform the same operation with the corresponding column vector. This video concludes our series of lectures on the NumPy library.